Hi, welcome to the statics tutorials. So in this one we have a particle equilibrium problem with a 782 pound weight being supported by 3 cables. And we want to find the force in each of the cables at equilibrium. So let's just assign A, B, C to the different locations. So we've got A, B, C, D, and E. And then we need to draw our free body diagram. So everything comes together here at A. So we use A as our point on our free body diagram. We have the 782 pounds going straight down. We have the force A to D. Let's see what other cable. We have this force A to C that we'd have to disconnect. So that would be another force in here. And if we're going to separate this particle out, we'd have to break this last connection, so I have this force A to B in there. Looking at our forces, we have our weight that's going straight down, so we know what direction it goes in. We've got this force A to D that looks like it's going in the positive Y direction. We've got this force A to C that's going in the negative X direction. So the only one that we need to do a position vector for is this force A to B. Let's draw that position vector over here. So we're going, let's see, looking in X. X is in this direction. We need to look for the line with the 2 arrows on it that's parallel to that, and that's our 3. So we're coming out from the origin 3. So it'll be a positive 3i. And then we're coming out from the origin 2 in the y direction, but it looks like it's moving in the negative y direction. So it's going to be a negative 2j. And then we're going up 4 meters, so it's going to be a positive 4k. And we can get the magnitude of RAB. And this gives us 5.385 meters. Now we can set up our force vector. So our force vector A to B is equal to magnitude of FA to B times the position vector divided by the magnitude of the position vector. And so with this, we're just going to take each of the components and divide by the magnitude. So we get 0.5571i, 0.3714j, and 0.7428k. And then we can go ahead and start with our sum of forces. Why don't we start with sum of forces in the z direction, because we know the 782, and A to B is the only force that has a z component. So that should give us our easiest equation. So we'll take our z component out, 0.7428 FAB. No force in the z component here. No z component in this force here. No z component in FAC. So the z component here is just going to be negative 782 pounds. We can now solve this for FAB by sending the 782 pounds to the other side of the equation, or by adding 782 to both sides and dividing through by the 0.7428. This gives us an FAB of 1053 pounds. And then we would typically go ahead and report this in kilopounds, so 1.05 KIP. Kilopounds, notice, is a mixed unit, so it's a metric prefix with an English system unit, but it is a unit that's used in the Hibbeler text, so we'll go ahead and use it here. Now we can do the rest of our equations. So sum of forces in y equals 0. FAD has that y direction, so it'll be FAD. And then we'll include the y component here, 0.3714 times 1053 pounds equals 0. And we'll get FAD then is 391. Since this is less than 1,000, I'm just going to go ahead and write it in pounds instead of writing it as 0.4 or 0.39 kilopounds. And let's do our sum of forces in x equals 0. So FAC was our force in the x. Since it's going in minus x, we'll write minus FAC. And then we'll do the x component here. And we can solve this for FAC, and we'll get FAC equals 587 pounds. All right, thanks for watching.